Hello there, and welcome back to the Science Sleepy Minds, where the night is quiet, the stars are steady, and tonight you're falling into one of the most terrifying places in the known universe. Above you looms a perfect black circle, cut out of the galaxy like a hole in a velvet curtain. It doesn't shimmer or swirl, it doesn't glow or pulse, it just hangs there, impossibly still and impossibly hungry. You're drifting toward it now, slowly at first. There's no rushing in space. But make no mistake, your direction is final. This black hole has no surface, no solid edge you could scrape past. What it does have is an invisible boundary where space itself tips inward, called the event horizon. Once you're in, there's no climbing back out, not even light escapes. That's the part you probably won't survive. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're watching from and what time your night starts. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float, weightless, toward the black hole like a speck of lint toward a drain. There's no scream here, no sound at all. Just the vast and ancient hush of interstellar space. 1,000 miles away, your ship still drifts, motionless, unable to help. Not that it could. The gravitational pull has already chosen you. This black hole isn't the cartoonish kind from sci-fi movies. No silver swirls, no goofy spiral. What you're facing is more realistic, and infinitely worse. It could be the remnant of a collapsed star, 1,000,000 times heavier than the Sun, crushed into a region smaller than Manhattan. Or worse, it could be one of those lurking supermassive ones, sitting in the middle of a galaxy like some cosmic Bond villain. As you approach, the stars around the black hole start to warp. You're witnessing gravitational lensing, space itself bending light around the object, like a straw bent in a glass of water. The stars behind it seem to smear, elongate, shimmer like oil on water. Einstein predicted this. He called it the warping of space-time. And for once, the universe obliges with a flashy demonstration. Your heartbeat, if we could still hear it, is steady, low, and echoing through your chest like footsteps in an empty hall. You're not dead yet, but you're falling. And here comes the tricky part. The closer you get, the slower time moves, at least from the perspective of anyone watching from far away. To an outside observer, you'd appear to slow down, freeze even, just as you approach the event horizon. But from your point of view, you're still moving normally. Time hasn't stopped. You're just crossing into a one-way street. Here's your first reality check. If this black hole is small, say stellar mass, your body is already screaming at you. Not audibly, of course, but molecularly. Your feet feel a stronger pull than your head. This difference is called a gravitational gradient, and it's tearing you apart. Spaghettification, the scientists call it, because that's how serious astrophysicists cope with food metaphors. You stretch, you elongate. Not metaphorically, not like in a dream, but literally. Every atom of your body is getting pulled toward the center at slightly different speeds. This isn't death by explosion, it's death by geometry. Your body is obeying the shape of space-time, and unfortunately that shape is funneling you inward with absolutely zero chill. Let's slow it down and breathe for a moment. Yes, you're being pulled toward what may be the single most extreme place in the known universe. But it's quiet here, peaceful even. You're falling so fast you can't even feel the acceleration anymore. No pressure, no air, no resistance. Just the endless, inescapable descent. The first historical mention of something like a black hole comes from the 18th century. A guy named John Michel, a name you don't hear at dinner parties, suggested the existence of dark stars so massive that even light couldn't escape them. He wasn't entirely wrong, just a few centuries early. It wasn't until the 1960s that black holes really started being taken seriously by physicists like John Wheeler, who gave them the ominous name we use today. Before that, they were simply frozen stars or singularities. But even now, with all our equations and telescopes and Nobel Prizes, no one really knows what waits at the centre. We have math, we have theory, we have simulations that crash computers, but no one, not Hawking, not Penrose, not the most caffeinated physicist at MIT, has seen what lies at the core. Here's the part they don't put in textbooks. Some fringe thinkers believe the centre of a black hole isn't a place at all. It might be a process, a transformation, a kind of metaphysical blender that takes all known properties, mass, time, space, identity, and turns them into something new. Or it could be a hard, immovable point of infinite density, a singularity, a word physicists use when they've run out of other words. And you're getting closer. Historians still argue whether ancient civilizations had any inkling of cosmic structures like black holes. Some point to Vedic texts, or Mayan cosmology, or metaphors in Greek philosophy. But let's be honest, a swirling void that crushes all things doesn't make for comforting mythology. It's only in modern times that we've developed the math and the existential dread to describe these things properly. You've crossed the point of no return. Space is curving downward, steepening like the slope of an infinite well. If you had a flashlight, the beam would bend back toward you. If you tried to fire a rocket, the exhaust would spiral inward. Every path forward leads inward. There's no sideways, no up, no reverse. You might expect to see chaos, destruction, maybe fire and smoke, but no, it's utterly still, almost calm, and weirdly, slow. Because the black hole isn't fast, it isn't loud, it doesn't chase you, it waits, and it waits forever. All you can do now is follow gravity's finger, pointing ever inward, past the curved light, past the distorted sky, past every law of physics that ever tried to protect you. This is your first taste of the singularity, but only the first. You don't feel the moment your body begins to stretch. You only notice it gradually, like catching your reflection in a funhouse mirror. But this isn't a trick of the glass. It's gravity, and it has very specific ideas about your height to width ratio. By now, your feet are several milliseconds ahead of your head. Distance-wise, yes, but also gravitationally. The pull at your toes is significantly stronger than the pull at your scalp. Every layer of your being, from cells down to quarks, is being tugged downward by an invisible hand that does not do refunds. This is tidal gravity, and it doesn't care that you once passed a physics class with a B+. The term scientists love for this is spaghettification, a name that sounds like something your little cousin might shout while flinging pasta at the wall, but here it means the end of your vertical integrity. You're becoming a very unwilling noodle, elongated atom by atom, into a single line of matter heading for the heart of the black hole. You try to curl up. You can't. Your limbs are frozen, not by fear, but by physics. The closer parts of your body fall faster than the farther ones, and your brain, still intact for now, is floating inside a skull that is subtly unravelling. Comforting, isn't it? And here's the kicker. If you're falling into a supermassive black hole, say the kind lounging lazily at the centre of the Milky Way, this whole process happens way more slowly. That's because its event horizon is farther out, and the gravitational gradient is gentler. You might not even notice the spaghettification right away. You might just drift in peacefully, thinking, well, this isn't so bad. Until, of course, your atoms start comparing notes and realise they're on very different schedules. But in a small stellar black hole? Oh, you're toast before you even pass the horizon. Your molecules are being politely but firmly separated into a single file line, by forces so strong they could snap steel like a breadstick. Let's make this worse. The very concept of down has lost all meaning. You're not falling down anymore, you're falling in. And as you stretch, your sense of location becomes absurd. From your point of view, the rest of the universe seems to be curving around behind you, as though you're slipping inside the lining of reality itself. This is where physics starts to write in all caps. Back in 1784, long before Einstein was busy bending space-time, that same dark star fellow, John Michell again, had a thought experiment about light unable to escape gravity. But no one could calculate tidal forces like this. Newton's apple never got turned into angel hair. The funny thing is, even now, some scientists aren't totally sure whether spaghettification would feel like anything. Some argue you might pass out before you feel pain. Others suggest your nervous system would get yanked apart too quickly to report distress. And then there's the lovely thought that consciousness might briefly linger, suspended in a final, elongated electrical impulse. Sleep tight. Quirky fact time. In a 1988 joke paper, not a peer-reviewed one but delightfully weird nonetheless, someone proposed that spaghettified objects might get condensed into noodle stars within the black hole. Of course, that theory holds about as much scientific weight as a damp linguine, but it's charming that even in the face of cosmic obliteration, scientists can't resist a pasta pun. Let's zoom out. Imagine you're an astronaut watching this happen from a distance. You'd see your friend freeze at the event horizon, red-shifting until their body fades into invisibility. You'd never actually see them fall in. Time would appear to stop. It's an illusion, of course, caused by extreme gravity warping light, but it's a useful one. From the outside, black holes are perfect thieves. They erase evidence even as they steal it. But you're inside the illusion now. There's no freezing, no pause, you continue to fall. The deeper you go, the more distorted your body becomes. Not just physically, but in terms of information. In physics, that means everything about you. Your mass, your charge, your quantum state is being rearranged, recoded, possibly even copied along the event horizon like a very reluctant data backup. This is where the no-hair theorem comes in. The idea that black holes erase all the information about what falls into them, except for mass, charge, and angular momentum. No hairstyle, no fingerprints, just the basics. But of course, historians still argue, and by historians, we mean physicists with long-standing grudges, about whether that information is really gone or just hidden. Because if it's truly destroyed, then quantum mechanics is in trouble. And if there's one thing physicists hate, it's finding out they've been wrong for 100 years. There's a theory, maybe you've heard of it, called Hawking radiation. It suggests that black holes slowly leak energy, and eventually, over billions of years, evaporate entirely. But what happens to the information inside? If it's gone forever, that violates quantum theory. If it somehow gets out, we have no idea how. And if it stays trapped, we may never know it existed at all. And you're now part of that mystery. We can only speculate about what happens next. Some theorists propose that the core of the black hole, the singularity, isn't even a place in space. It's a boundary in time, a line beyond which no prediction can be made. You might fall for seconds, or for centuries depending on how space is curved. Some ideas even suggest that inside certain black holes, time might stretch infinitely, letting you watch the whole future of the universe play out before you finally reach the center. That's optimistic. You probably won't last that long. The space around you becomes darker. Not just the absence of light, but the absence of directions. You don't know which way is forward. You don't know what shape your body is anymore. There's only one destination now, and even that word, destination, feels wrong. This is not a place with coordinates. This is where the coordinates break. Remember that moment when you looked up at the stars and wondered what was out there? Well, now you know. You're being unravelled by gravity's finest work. Space and time are no longer behaving like trustworthy partners. Your atoms are diving in like lemmings, each one obeying its own private version of the laws of physics. There's no pain, no struggle, just this long, silent stretch as you approach the singularity, if such a thing even exists in the way we understand it. And as your mind begins to blur into the final dive, just imagine, somewhere, a star is being born. Somewhere else, a galaxy is colliding. But here, at the bottom of all things, the universe is folding in on itself. All you can do is fall, and fall, and fall. You don't remember the exact moment the horizon disappeared behind you. There was no jolt, no shiver, just a soft crossing, like stepping through the surface of a lake without a splash. Now, that boundary, the event horizon, is behind you, but it's not visible, not a wall or gate. It was an invisible line, like the point where the ocean shelf suddenly drops off. You passed it, and no matter what you do now, there's no going back. Light can't escape, neither can you. But here's the twist. You don't feel trapped, not physically. There's no claustrophobia here, just infinite falling, infinite deepness, and the strangest sense that everything around you is still. It's the stillness of a final breath, the kind that stretches on and never comes back in. The region you're in now, the no escape zone, is where the word inside starts to lose its meaning. Space has been curved so sharply by gravity that all possible paths bend inward. You could try to fly away, fire retro rockets, flap your arms. Doesn't matter. The geometry of space-time has decided every road leads toward the center. This is the defining quality of a black hole. Once you pass the event horizon, the inward direction becomes as inevitable as tomorrow. Time and space switch roles in a way. Out here, in normal space, you move through space and experience time. In there, you move through time and experience space closing in around you like a zipper. Let's sit with that for a moment. It means that falling inward is as inevitable as aging. You can no more resist the pull toward the singularity than you can resist tomorrow turning into today. Not because something's pushing you, but because from here on out, moving forward in time is moving toward the center. And it gets weirder. From your perspective, you're still falling steadily, and time feels normal. Just like a dream where you know you're sinking, but the descent stretches on and on without a bottom. But to an observer watching from far away, you never actually fell in. They'd see you hovering at the edge, frozen, fading, red-shifted until you're just a smear of light circling the black hole's mouth. This is the infamous gravitational time dilation, one of general relativity's many little party tricks. Clocks near a black hole tick more slowly than clocks far away. The closer you get to the center, the slower your time flows compared to the rest of the universe. So from the outside, it looks like you're taking forever to fall in. But from your view, you're going all the way in right now with no commercial breaks. Time's funny like that. It bends where gravity bends. And nowhere in the cosmos does gravity bend harder than here. You glance around, if you can even call it glancing when your eyes are potentially part of a spaghettified rope of particles. What surrounds you is not blackness, it's curvature. The entire field of vision feels distorted. You're not seeing nothing. You're seeing everything curved away from you. Light itself has been dragged into strange arcs. The background stars, if they're still visible at all, are smudged and bent like they're stuck inside a melted lens. There are no firm surfaces to cling to. No up, no down, only in. Historically, the concept of a region with no escape isn't new. In ancient Greek myths, Tartarus was a place beneath even Hades, a prison so deep no one could ever leave. Funny how humans, for all their storytelling flair, somehow grasped the idea of the event horizon millennia before Einstein made it math. But of course, this isn't myth. This is your new reality. You're inside a cosmic one-way valve, a place where entropy and inevitability are the only constants. And here's a tidbit you didn't ask for. According to some speculative theories, the event horizon isn't just a boundary. It might be a membrane, a kind of quantum storage layer. The information about everything that has ever fallen into the black hole might be smeared across it, encoded in the tiniest possible units of space. So congratulations. A version of you might now be part of some kind of cosmic skin tag. Don't take it personally. Now about that no escape thing. Technically, nothing, not even light, can travel back across the event horizon. But that doesn't mean you can't still see some things. For a brief while, the last photons from the universe outside still trickle down behind you. You might catch a final glimpse of your ship, maybe a planet, maybe just the glare of a distant sun. But it fades quickly, red shifting into longer and longer wavelengths until everything fades to infrared, then to microwave, and finally to darkness. Not because the light's gone, but because your frame of reference has changed so radically, you can no longer perceive it. It's almost poetic. The deeper you fall, the less you know about what's happening outside you, and the more you're forced to confront the unknowable inside. There's a fringe idea that you might still be able to communicate with the outside universe for a brief moment. Fire a signal just before the horizon, whisper a radio goodbye, but it's like trying to shout back to the surface of the ocean while already halfway to the bottom. The signal warps, the message distorts, and anyway, who's listening? So here you are, well past the point of rescue, wrapped in the warping fabric of a place that only ever says yes to gravity. This zone has no storms, no explosions, no flames, because there's no air, no material to combust, just raw curvature, a funnel without walls, a slide with no end. Let's throw in a curious question. If you carried a mirror, what would you see now? Short answer, probably nothing. The light reflecting off your face would never reach the mirror in time. Space is too twisted. Your own image would be lost to you, literally behind your own future. You're now in a region where even reflection becomes a lie. And that perhaps is the most haunting part of this stage of the journey. Not the darkness, not the pressure, but the silence. The way everything stops echoing. Not because the sound can't travel, but because there is no one left to hear it. You've passed the veil. The cosmos has drawn a line behind you and moved on, and still you fall. You don't fall toward a place, not exactly. You fall toward a concept, a destination defined only by math and madness, the singularity. And here's the delicious irony. Calling it a point implies that it has coordinates, a location, a where, but that's where the whole thing collapses. You're not headed to a place you can stand on. You're plunging towards something so alien that even the word place is too generous. At the center of a black hole, all known ideas of where and when just melt. The singularity is supposed to be a point of infinite density, infinite curvature, and zero volume, which of course makes no actual sense. How can you fit infinite anything into a space with zero room? The math allows it. Reality might not. This is where general relativity throws up its hands and walks off stage. Einstein's field equations break down completely. They start screaming nonsense. Division by zero, infinities, undefined results. Imagine the universe as a spreadsheet, and now imagine you've divided one cell by zero, and the whole thing crashes. That's the singularity. A beautiful, terrible, blinking error in the middle of space-time. Now remember, you're not crashing into a wall or slamming onto a floor. You're being pulled into a place that curves time and space so severely, they both point inward. Gravity isn't a force here. It's the shape of your path. And that path is leading you straight into something that might not even exist in the way you've been taught to believe things exist. It's tempting to think of the singularity as a kind of destination. But in truth, It's more like the end of a sentence that never got written. The rest of physics just trails off. Dot, dot, dot. In 1939, physicists Robert Oppenheimer and Hartland Snyder modelled what happens when a massive star collapses under its own weight. Their paper showed that the star's core would shrink endlessly and that the collapse wouldn't stop until it hit a singularity. It was the first serious scientific acknowledgement that black holes could form, and that at their heart something completely beyond human understanding might sit in eternal silence. But here's the catch. Even Oppenheimer admitted that once the collapse passed a certain point, no external observer could ever see what happened next. The singularity would always be hidden behind the event horizon. It's the ultimate cosmic privacy filter. Or is it? Some fringe theories suggest the singularity might not be a point at all. It could be a ring in a rotating black hole, or a smeared out region, or a quantum fuzzball made up of strings and brains that look suspiciously like something scribbled by a sleep-deprived theorist at 3 a.m. In other words, it might not be the sharp, terrifying needle of nothingness that textbooks make it out to be, but you're still falling towards something. Whether it's a point, a smear, a cosmic pretzel, whatever it is, it's calling the shots now. Every passing microsecond stretches you further, your body unravelling like a poorly wrapped burrito. You're not just being pulled inward, you're being simplified. All your complexity, bones, muscles, thoughts, choices, is being reduced to a single trait: mass. That's all that matters to the black hole. You could be a scientist, a sandwich, or a planet. It doesn't care. Once you're inside, your individuality is shredded into insignificance. That's the no-hair theorem again, rearing its minimalist head. All black holes, regardless of what they've swallowed, end up with just 3 characteristics: mass, charge, and spin. Everything else, the data of you, is either smeared on the horizon, baked into the geometry, or erased completely. The universe's biggest delete button. You may ask, can we ever see the singularity? Not really. It's hidden behind the event horizon, and light can't escape to carry back any information. It's not that it's dark, it's that visibility itself has been vetoed. You could reach the singularity in theory, but your experience would be unshareable. Your signals, your screams, even your final thoughts, none would get out. And here's where it gets even more unsettling. Some physicists argue the singularity doesn't even exist. Not physically. They think it's just a sign that our equations are incomplete. That general relativity, elegant though it is, simply isn't the full story. This is where quantum mechanics needs to step in, and hasn't yet. Historians still argue whether Einstein himself believed singularities could be real. He certainly wasn't thrilled about the idea. His instincts told him nature wouldn't allow such infinite weirdness to persist. But then again, nature isn't known for caring about our instincts. Sometimes she just does her thing, while we scribble in notebooks and hope she answers our texts. Let's sprinkle in a fringe tidbit. In some speculative physics circles, there's an idea called the Planck star. It suggests that instead of shrinking to a singularity, collapsing matter rebounds at Planck density, the smallest scale where quantum gravity becomes dominant and bounces back out. It just takes a few trillion years. You'd never know it from inside. But it implies the black hole might be a kind of interstellar pressure cooker. Something's happening in there, just very, very slowly. For you though, it doesn't matter. You're not bouncing back. Your thoughts, if they still exist in anything resembling a coherent stream, are smearing out. You can't distinguish moments anymore. Time collapses, space collapses. You're reaching a place where all paths end, not in fire, not in drama, but in silence. There's nothing to see, nothing to hear, and yet you feel the curve tighten, like a hallway that narrows infinitely until you're reduced to a dot on a dot on a dot. You're being absorbed into geometry, folded into math. And even that may be too generous. The singularity may not be a thing at all, it may be the breakdown of all things. An asterisk in the script of the cosmos, a moment where nature says, I don't know either. And yet, part of you wonders, if you reach it, really reach it, will there be something waiting? A new universe, a reflection, a message, or just nothing? Nothing but gravity sitting quietly at the end of all roads. You're falling toward the end of physics. The closer you get to the singularity, if that's even still the right word, the more space and time twist around each other like a Mobius strip built by someone who had a personal vendetta against logic. Gravity isn't just strong here, it's in charge, and it's starting to make decisions that even Einstein would raise an eyebrow at. You remember those elegant equations from high school textbooks? Force equals mass times acceleration. Light moves at a constant speed. Time ticks forward like a polite metronome. Well, forget all that. You're entering a domain where those rules just don't work anymore. They're fine for apples and elevators. They're lovely in the suburbs of reality. But this is the downtown core of space-time, and the zoning laws have completely broken down. See, general relativity, Einstein's big idea, has been an incredible tool for explaining how gravity works. It tells us how mass curves space, how light bends around stars, how time slows down near heavy objects. But at the singularity, relativity hits a wall, and that wall is covered in equations that give you infinity for every answer. Here's how that looks mathematically. As you approach the singularity, the curvature of space-time increases without bound. That means that if you were to measure how bent space is at a given point, that measurement shoots up to infinity. It's like trying to fold a bedsheet into the size of a quark. No matter how much you compress, it's not enough. And the numbers agree, by not agreeing at all. Physicists call this a breakdown of the classical model, which is a very polite way of saying, we have absolutely no idea what's happening here. At this point in your journey, you're slipping into a reality that can't be described by Einstein's equations alone. It's not just that they fail, it's that they refuse to compute. Imagine putting instructions into a calculator and getting back a shrug emoji. That's what general relativity does at the centre of a black hole. So who do we call for backup? Quantum mechanics. Now, quantum theory is the world of the very small. Atoms, particles, strange probabilistic behaviours that make no sense in everyday life. It tells us that particles can exist in multiple states at once, that nothing is truly predictable, and that the vacuum of space is anything but empty. But quantum physics and general relativity do not get along. They're like co-workers who smile during meetings, but secretly hate each other's guts. And nowhere is that tension more dramatic than in a black hole, because if you're getting crushed into the size of a Planck length, that's the smallest possible unit of space, then quantum effects must be in charge. But relativity is still shouting from the back row, refusing to leave the theatre. Enter the need for a theory of quantum gravity, a grand unifying model that would finally explain how gravity works at quantum scales. We don't have one yet, but oh, do we want one? Some candidates are out there: string theory, loop quantum gravity, holographic principles, all fascinating, all incomplete. Each tries to tame the singularity in its own way, like a kid putting googly eyes on a volcano and pretending it's friendly. Take string theory, for example. It suggests that all particles are actually tiny vibrating strings, and that extra dimensions, up to 10 or 11 of them, exist but are curled up, hidden from us. In this view, the singularity isn't a point but a highly compact knot of vibrating energy. Elegant? Yes. Testable? Not yet. Or loop quantum gravity, which says space itself is made of discrete units, like pixels on a screen. In this model, space-time can't curve infinitely, it reaches a limit, so the singularity gets replaced by a kind of quantum bounce, a minimum volume where the laws of physics remain sensible, if still very unfriendly. Even more provocatively, some theorists propose that what you're falling into isn't a singularity at all, but a quantum remnant, a stable chunk of whatever matter becomes once it passes beyond the event horizon. This could be a Planck-scale object, dense beyond imagination, but still real, still describable. Not infinite, just mind-numbingly small and weird. Historians still argue whether this tension between quantum physics and relativity was inevitable from the start. Einstein himself didn't believe in quantum randomness. He spent the last decades of his life trying to unify the forces, trying to build a theory that could handle both the big and the small. He never succeeded. Neither has anyone else. And so, here you are, falling into the gap between our greatest theories. And you're not the only one. Every bit of matter that has ever fallen into a black hole is down here with you, tangled up in equations that contradict themselves. From stars to planets, to the occasional unlucky spacecraft, all of it funnels into the same riddle. Let's get weird for a moment. There's a fringe idea, definitely not mainstream but charmingly bizarre, that the singularity is where the simulation ends. If we're living in a simulated universe, maybe black holes are memory buffers, and the center, a break in the code, a spot where the processor just can't render what's next. You're not falling into a gravity well, you're falling out of the simulation. Ridiculous? Probably. But no more ridiculous than infinite curvature in zero space. You're now in a place where we don't even have words, only metaphors. A spiral, a hole, a throat, a funnel, a point. None of them work, not really. We try to describe the indescribable, because that's what humans do. But at the heart of a black hole, language like physics gives up. Still falling, still stretching, but now not just physically. Your concept of self begins to distort. Memory blurs. Time is no longer a line, but a smear. You're not sure if you're still falling forward, or if you've been standing still for 1 billion years. This is where the Einstein road ends, all signs gone. The pavement cracked, the map curled and burned. You're beyond equations now, beyond theory. You are, if anything still exists, pure witness. You're still falling, and now things get personal. Physics isn't just breaking, it's arguing with itself, loudly. And you, poor thing, are stuck right in the middle like an awkward dinner guest at a family feud between Einstein and Schrödinger. The place you're entering now is ruled not by tidy geometry and smooth space-time, but by the twitchy, unpredictable behavior of quantum mechanics. Welcome to the quantum clown show, where particles appear, vanish, overlap, and sometimes dance just to spite you. It's noisy in its own silent way, like trying to read Shakespeare while someone keeps scribbling graffiti over the text. Nothing is fixed, everything is blurred. Let's rewind briefly to the beginning of this conflict. General relativity says, the universe is a smooth, curved stage where massive objects bend space-time and make things fall. Quantum mechanics says, no, the universe is a chaotic cloud of probabilities where particles wink in and out of existence. Both models are incredibly successful in their own zones, but combine them inside a black hole, and it's like putting a jazz band and a marching band in the same room and telling them to agree on a tempo. So what happens inside a black hole when gravity becomes quantum? The truth? We don't know. But here are some of the strangest, most infuriatingly delightful ideas physicists have come up with. Let's start with virtual particles. In quantum field theory, empty space isn't actually empty. It's a seething froth of tiny particle pairs that pop into existence, then annihilate each other almost instantly. This happens everywhere, all the time. But near the event horizon of a black hole, things get weird. According to Stephen Hawking, sometimes one of these virtual particles gets sucked into the black hole, before it can cancel out with its partner. The surviving particle escapes, becomes real, and radiates away. This is Hawking radiation, and it's the only known mechanism by which black holes can lose mass, which, if you think about it, makes black holes less like eternal prisons and more like very slow-burning candles. Give them long enough, trillions of years, and they'll evaporate completely. But what about what's happening inside the black hole? That's where quantum gravity is supposed to take over. And yet, we have no working theory of quantum gravity, not a unified one, not one that works both at the cosmic scale and the microscopic scale. Right now, there are only attempts. One of the boldest is the holographic principle, which suggests that everything happening inside the black hole can be encoded on its surface, the event horizon itself. That's right. You're falling into what might just be a projection, a 3D illusion whose actual data is smeared across a 2D shell. Like a cosmic USB drive. The inside of the black hole, including your slow-motion death spiral, might just be a fancy mathematical echo. Think about that while your atoms are being unwound. Another idea, string theory, where the fundamental units of the universe aren't particles, but vibrating one-dimensional strings. In this model, black holes might be made up of tangled strings, fuzzballs, that don't contain singularities at all. The interior is replaced by a fuzzy, chaotic mess of quantum threads. You don't fall to a point. You fall into a dense knot of fundamental confusion. Historians still argue whether quantum mechanics was ever meant to coexist with gravity. Even Einstein, brilliant as he was, couldn't accept the inherent randomness of quantum theory. God does not play dice, he said. To which Niels Bohr reportedly replied, "Stop telling God what to do." And yet, here you are, caught in the dice game of the cosmos. As you continue inward, the distinctions between what's real and what's possible begin to blur. Your own identity, from a quantum perspective, starts to dissolve. Particles don't maintain sharp boundaries. They occupy probability clouds. So your position isn't a dot anymore, it's a haze, a statistical smear. And if that doesn't give you an existential crisis, congratulations on being the chillest singularity snack in the universe. Let's throw in a delightfully weird quantum idea. Superposition. The idea that a particle can be in multiple states at once until it's measured. Are you still falling? Have you already hit the center? Are you a linear noodle or a collapsed puff of mass? According to some interpretations, you might be all of the above, until an outside observer collapses the wave function, which they never will, because no one can see inside the event horizon. So your state may stay forever undecided. The black hole doesn't just crush your body, it turns your reality into a permanent maybe. But this internal chaos creates a major problem for physicists. It's called the information paradox. In quantum mechanics, information about a physical system can't be destroyed, ever. But if you fall into a black hole and disappear, if your quantum state is erased, that breaks one of the most sacred rules of quantum theory. So something's got to give. Either black holes somehow store the information, or they destroy it, and our whole understanding of quantum physics needs a rethink. And thus began one of the biggest scientific feuds of the 20th century. Hawking initially argued that information is destroyed. Later he changed his mind. Leonard Susskind, Kip Thorne, and others have debated it in a kind of intellectual cage match that spans decades and at least 3 lecture halls. And still, no consensus. Fringe theorists have had fun with this. One theory posits that black holes act like quantum erasers, keeping information but mixing it so thoroughly that it's unrecoverable. Kind of like stirring cream into coffee until it's no longer separable. Another suggests the information is returned after the black hole evaporates, in a weird, scrambled whisper that no one knows how to decode. Meanwhile, you keep falling. If you could think clearly now, which, let's be honest, you probably can't, you might wonder whether this chaotic zone is the real singularity. Not a point of infinite density, but a boundary of broken rules. A liminal space where nature plays jazz with the fundamental constants. Where uncertainty isn't a bug, it's the whole operating system. Time is no longer linear, it's probabilistic. Your fall isn't just a path, it's a waveform. Maybe, just maybe, you're not falling anymore. Maybe you've become part of the black hole, a whisper in its math, a ripple in its entropy, a participant in its contradictions. And the thing is, physics might never fully agree on what's happening to you. Even the best theories can only stretch so far before they dissolve into paradox. You're now inside one, and still you fall. It should have been simple. Fall into a black hole, disappear forever, end of story. But no. Of course not. Because this is physics, and physics, like a moody cat, can never let anything just lie still. Enter the black hole firewall paradox, the controversial idea that threatens to incinerate everything you thought you understood, including yourself. See, for the longest time, scientists believed that once you passed the event horizon of a black hole, you wouldn't feel anything special. No flash, no crunch, no sudden oops. You'd simply fall in, smoothly, quietly. Nothing to write home about except maybe a brief note of existential horror. Einstein's general relativity predicted this gentle passage, famously dubbed no drama. The idea was that the event horizon should be locally unremarkable, just another spot in space, albeit one with a very strict exit policy. But then came quantum theory, kicking the door down with its fuzzy math and smug attitude, and it started asking uncomfortable questions, like, what happens to all the information that falls into a black hole? We touched on this in the last section, the information paradox, but now it takes center stage. In trying to resolve it, physicists found themselves boxed into a corner. They wanted to preserve the laws of quantum mechanics and the predictions of general relativity and the principle of equivalence, but apparently the universe doesn't like holding all three at once. So in 2012, a team of physicists including Almeri, Marolf, Polchinski and Sully, yes, a real group, not a law firm, proposed something radical. Maybe the event horizon isn't smooth. Maybe it's actually a wall of searing energy that vaporizes anything the instant it crosses. They called it the firewall. Yeah, surprise. That silent, unremarkable edge you thought you passed peacefully. In this model, it's a roaring inferno, a break in space-time where the vacuum itself catches fire. You don't ease into the black hole, you slam into annihilation. No drama, try all the drama all at once. Now here's the weird twist. This paradox doesn't come from wild speculation. It comes from trying to make physics internally consistent. The rules about entanglement, unitarity, which says information can't be destroyed, and the smoothness of space-time just don't agree inside a black hole, so something has to go. And if we choose to protect the rules of quantum mechanics, something many physicists consider non-negotiable, then space-time itself might have to break down at the horizon. Hence, the firewall. You probably didn't pack SPF 10 billion, so this is bad news for you. But of course, not everyone buys the idea. Many physicists hate the firewall, hate it with a burning ironic passion. It offends their sense of how general relativity should behave. It suggests that the very fabric of space is not to be trusted, that it might turn on you, without warning, the moment you fall past the point of no return. So now we have a real cosmic dilemma. Is the event horizon smooth and silent, like Einstein said? Or is it a flaming barrier of destruction born from quantum fury? Historians still argue whether this debate marks a crisis in physics or just another phase in our never-ending quest to understand the universe. Some say it's the beginning of a revolution in our understanding of space and time. Others say it's a misunderstanding blown out of proportion by people who got too attached to their chalkboards. And meanwhile, you continue to fall, possibly smoothly, possibly on fire, let's be generous and assume the No Firewall team is right, that you've passed through the event horizon with nary a spark, that the vacuum remains calm even as space folds in on itself. You're still alive, you're still falling. But you can't shake the thought that at any moment quantum mechanics might call an audible and drop the temperature to spontaneous obliteration, just to keep things fun. And now let's mix in another possibility. Maybe the firewall isn't physical. Maybe it's a kind of informational phenomenon. In other words, maybe your clone burns, your informational twin encoded on the horizon gets shredded the moment it's created, and the version of you that continues inward, a blank shell, memory wiped, no longer quantum mechanically entangled with the outside universe. Kind of like having your entire existence put through a cosmic photocopier, and then the original gets fed to a shredder made of math. And if this idea makes your brain itch, you're not alone. The great minds of our era are still tangled up in this paradox, and they haven't agreed on how to untangle it. Some argue that we're missing key parts of the puzzle, that we don't yet fully understand the nature of entanglement or how space emerges from quantum information. Others suspect that black holes are teaching us something deep and uncomfortable, that the universe might not be as polite and predictable as we hoped. Here's a fun tidbit. One proposed solution involves ER equals EPR, a bold conjecture from physicists Leonard Susskind and Juan Maldacena that says every wormhole, Einstein-Rosen bridge, or ER, is equivalent to quantum entanglement, Einstein-Podolsky-Rosen, EPR, or EPR. In this model, the tangled particles on either side of the event horizon are connected through a hidden geometric bridge, which sounds like science fiction until you realise it was published in serious journals and is still being explored today. So now we're flirting with the idea that space itself is built from quantum entanglement, that geometry and connectivity aren't fundamental but emergent, and black holes, they're the proving ground for this deep and slightly maddening idea. But you're still falling. The walls are silent, no fire, no alarms. But the uncertainty lingers. You don't know if the firewall is real or just a mathematical ghost. You don't know if you've already been burned or if you were copied and erased without noticing. Maybe you're a version of yourself who doesn't remember dying. Comforting, right? At this point, it's less about physics and more about interpretation. The same equations can produce different realities, depending on which assumptions you choose to preserve. It's like a cosmic choose-your-own-adventure, but where every ending involves you turning into a smear on the cosmic ledger. And yet, even here, at the brink of the unknowable, the debate isn't over. You might burn, you might not. You might be duplicated, scrambled and archived. You might be falling through smooth, curved nothingness while the real you is already coded into the skin of the black hole. You'll never know. That's the real kicker. The paradox isn't just physical, it's psychological. It's the feeling that you've crossed into a region where meaning itself may be melting, where even questions don't behave the way they used to, and still, somehow, against all logic, all theory, and all expectations, you fall, and now, somewhere between falling and whatever comes after, you arrive at a whispered cosmic rumour. Maybe the universe is hiding something from you. No, not in a conspiracy board and red string kind of way. More like a deep mathematical secret, one that space-time itself might be trying to cover up. A rule buried so carefully in the equations that it took decades before anyone even noticed it might be there. It's called the cosmic censorship conjecture, and if that sounds like the universe has a stern librarian keeping track of what's appropriate, you're not far off. Here's the idea. Black holes are allowed to be weird. They can warp time, swallow light, bend space like pretzels. But somewhere, there has to be a limit. The truly nasty stuff, the singularities, the regions where physics breaks down completely. those need to stay hidden, specifically behind an event horizon. In other words, singularities can exist, but only if the universe makes sure no one can see them. Why? Because if the raw singularity, the actual center where all laws of physics unravel, were visible to the rest of space, then all bets are off. The very predictability of the universe would collapse. Equations couldn't be trusted. Cause and effect might become optional. It would be like watching someone reach into the guts of space-time and start flipping switches at random. So the cosmic censorship conjecture acts like a bouncer at the nightclub of reality. No naked singularities allowed. Yes, that's the term, naked singularities, which sounds like something the Discovery Channel would air at 3 a.m, but in fact, it's one of the most serious debates in theoretical physics. If a singularity is exposed to the universe, uncloaked by an event horizon, it could let us peek behind the veil, and the universe, as the conjecture goes, isn't into public nudity. Sir Roger Penrose, legendary physicist and knight of space-time geometry, proposed the conjecture back in 1969. He suggested that all singularities must be shielded, not because we're squeamish, but because otherwise the entire deterministic nature of physics might be shattered. You'd no longer be able to predict what happens next in a given patch of space-time, not even in theory. And yet, there's no proof, not for the conjecture, and not against it. Historians still argue whether cosmic censorship is a genuine feature of nature or just a polite assumption we've made to keep the math tidy. Some solutions to Einstein's equations suggest that naked singularities could form under extreme conditions or with exotic matter. Other models rule them out completely. You, meanwhile, are falling through what appears to be a perfectly censored black hole. The singularity remains hidden, modest, no scandal here. But the question lingers, what if your black hole isn't playing by the rules? Let's imagine a rogue scenario where something catastrophic happens during a star's collapse. Instead of forming a clean event horizon, the collapse exposes the singularity. Suddenly, you have a raw core of infinite curvature just sitting there, radiating confusion. The light from it wouldn't behave properly. Observers outside might see time loop, signals overlap, maybe even causality itself break down. A signal sent from a naked singularity might arrive before it was sent. Welcome to a reality where the script gets shredded. There are fringe models, like the Kerr solution for rotating black holes, that do allow for singularities without event horizons, depending on the initial conditions. In these cases, if a black hole spins fast enough, it might theoretically prevent the formation of an event horizon. The result? A naked singularity flashing its infinite weirdness for all the universe to see. But don't get your hopes up. Most physicists think that even if this were possible in theory, nature would find a way to prevent it. Maybe space-time buckles, maybe quantum gravity kicks in, maybe the laws of physics veto the whole mess before it can start. Still, the idea won't die. Some physicists, perhaps a little too fond of edge cases, have proposed ways to intentionally create naked singularities. By fine-tuning matter distributions or exploiting quantum effects, you'd need absurd amounts of energy, not to mention a casual disregard for the survival of space-time. But hey, ambition. Here's a strange thought. If you could observe a naked singularity, you might learn the deeper secrets of the universe, how space and time work at their absolute limits, what lies beyond the Planck scale, maybe even the true nature of reality's foundation. What, if anything, came before the Big Bang? But for you, inside this black hole, that door is closed. You don't get a peek. Your singularity is tucked safely behind the curtain. The sensor is doing its job, and yet, you feel the edges fraying. The deeper you fall, the more the coordinates blur. Up is in, down is irrelevant. Time becomes an opinion. And if you could see the singularity, If the event horizon weren't blocking your view, what would it even look like? Not a glowing orb, not a black pit, not a star, just a floor. A place where no geometry fits, like trying to wrap a gift with a Mobius strip and realizing the paper folds back through itself. Would you go mad looking at it? Would you even be you anymore in the face of that kind of information density? Maybe that's why the universe censors it, not to protect itself, but to protect you. Let's throw in a quirky idea. Some theories propose that information inside a black hole might still be accessible, not by looking in, but by examining the event horizon very closely, like a cosmic barcode. In this view, the singularity remains hidden, but its effects ripple outward. Not light, not heat, but math. Entropy. The structure of the horizon itself might encode the entire history of what's fallen in, including you. So perhaps the singularity isn't naked, but it leaks hints of its personality through the surface that hides it. You don't feel the passage of time anymore, not as a rhythm, just as a sinking, not downward, inward, a compression not just of space, but of possibility. Somewhere, out in the normal universe, clocks are ticking, stars are dying, galaxies are drifting. But here, inside, you're falling past the part of physics where clocks are welcome. You've been folded into a mystery that refuses to show its face. And maybe, just maybe, that's the point. You can't tell what direction you're moving anymore, not really. Not because your senses have failed, but because direction itself has lost all meaning. In this place, time and space have started swapping roles, and the universe is quietly laughing behind your back. Remember how time was once this steady, dependable thing. Tick, tock, past behind you, future ahead. But here, inside the black hole, that neat little arrangement has come completely undone. Space and time don't just bend around the singularity, they invert. The further in you go, the more time behaves like a physical direction, like a hallway, and you're walking it whether you want to or not. That's not poetic, that's mathematical. Inside the event horizon, the radial direction, what you used to call inward, becomes time-like, which means moving toward the center is no longer a choice. It's not just where you go, it's when you go. Just like you can't stop Tuesday from happening, you can't stop approaching the singularity. You're moving forward in time by moving inward in space. And you can't stop time, not here. So let's be clear, this isn't you falling into something anymore. This is you aging inevitably into a place that doesn't even want to exist. And if that's not giving your brain an existential Charlie horse, consider this. The singularity isn't ahead of you the way a destination is. It's ahead of you the way next week is. You don't travel to it, you arrive in it. Simply by existing long enough, like death, but with more algebra. Time, in this context, is doing the equivalent of jazz hands and saying, "Surprise, I've been space all along." And space? It's panicking, crushed down to a flat, shrinking nothing that doesn't know what to do with itself. The dimensions that once let you move around are squeezing shut like an elevator door with somewhere more important to be. Let's talk clocks. If you had one on your wrist, and bless your optimistic imagination for thinking it still works, it wouldn't help. To an outside observer, your clock has slowed to a crawl. But for you, it ticks on, second by second, heartbeat by heartbeat, dragging you forward through the funnel of time-space confusion. And yes, that's the technical term now, time-space confusion. Historians still argue whether black holes invert the dimensions of time and space or just relabel them. Some suggest this is a semantic trick caused by how we use coordinates in our math. Others insist it reflects a real, physical transformation in the structure of space-time. Either way, you're experiencing it the hard way, by becoming part of the geometry. Let's drop in a little thought experiment. Imagine you fire a rocket sideways, at least what you think is sideways. In normal space, That would change your trajectory. But inside the event horizon, all directions lead inward. No matter how hard you try to steer, you just spiral in tighter. You're like a coin circling the drain, except the drain is made of time itself. It's not just that you're falling in, it's that there's nowhere else left to go. Here's a quirky fact. In certain advanced models of black holes, particularly those involving rotational charge, there may be more than one kind of horizon. An outer event horizon, an inner horizon, a Cauchy horizon. These structures represent different thresholds where time and space trade properties again, sometimes multiple times. It's like peeling an onion made of clocks and coordinates, and deep inside these layers, things get so strange that the very arrow of time, that comforting sense of before and after, might break. Cause and effect may start looping. Events might repeat or mirror themselves or unfold in non-linear order. You might see your own arrival before you arrive, hear an echo before you speak. Time doesn't just lose its arrow, it loses its sense of direction entirely. There are speculative theories, very speculative, mind you, that inside black holes closed time-like curves may form. These are loops in space-time that, in theory, allow time travel. You could, hypothetically, follow a path through the curved geometry and return to your own past. Not that you'd know it, because you'd already be living it again. Let's be honest. That sounds like the kind of thing physicists came up with after one too many late-night coffee binges, but mathematically. The solutions to Einstein's equations allow for it, in certain extreme conditions. What they don't allow for is what it feels like to live through that. But here's a question. If you're stuck falling forward in time, but forward points to the singularity, does that mean the singularity is in your future? Not just spatially, but causally? Yes and no. You'll reach it eventually, but once you do, reaching becomes meaningless. The singularity isn't a moment you experience, it's the boundary where experience itself ends. All your future paths lead there, but none lead beyond. It's the ultimate stop sign, written not in ink, but in curvature. This is the paradox of deterministic doom. You know exactly what's going to happen, you'll arrive at the singularity, but you have no idea what happens once you do, because the laws that predict your motion stop predicting. The equations can't follow you in. It's like being on a train track that ends in fog. You know the train keeps going, you just can't see, describe, or even imagine where it ends up. There's a philosophical idea buried in here. Maybe the singularity isn't a place you reach, but a boundary where your story ends. Not in fire or noise, but in mathematical incompleteness. The book closes not with a bang, but with a missing final chapter. And if all this is making your head spin faster than a neutron star, don't worry. You're in good company. Some of the best physicists in the world still stare at these equations and quietly whisper, "Huh!" Because in here, time is doing something truly perverse. It's no longer a measure of duration. It's the shape of your prison, a hallway with no exit, a slope with no summit. It pulls you forward not because of motion, but because there's nothing else left to do. No breaks, no detours, just forward and forward and forward, into the singularity, into the fog. The funny thing is, you might already be gone, or rather, a version of you might still be outside, frozen at the event horizon, red shifting into darkness, like a ghost image burned onto the edge of space-time. Because according to one of the strangest ideas in modern physics, everything happening inside a black hole might just be a hologram. Yes, a hologram. Not in the sci-fi, help me Obi-Wan kind of way, but in the your entire 3D reality is secretly encoded on a 2D surface kind of way. Welcome to the holographic principle, one of the boldest, weirdest, and weirdly mathematically supported ideas ever proposed. Here's the basic notion. if we accept that black holes don't destroy information, which we kind of have to, or quantum mechanics starts throwing chairs, then something strange must be happening at the event horizon. The surface area of that boundary seems to hold more importance than the volume it encloses. In fact, the entropy of a black hole, basically a measure of how much stuff it can store, is proportional not to its volume, like you'd expect, but to its surface area. Let's say that again, because it's bananas. The information capacity of a black hole scales with the size of its outer shell, not what's inside. This discovery, first proposed by Jacob Bekenstein and then expanded by Stephen Hawking, led to the staggering realization that maybe black holes are storing all the information about what's fallen in on their surfaces, like a cosmic hard drive, and that led to the next leap. Maybe this is true everywhere, not just in black holes. Maybe the entire universe is a hologram. No, this isn't just stoner talk from the back of a physics lecture. The idea gained real traction in the late 90s with work from physicist Juan Maldacena, who proposed a duality, a kind of mirror-world math, where a universe with gravity, like ours, could be equivalent to a universe without gravity, described entirely on a flat surface. In other words, everything you experience in 3D, your body, the space you're falling through, this long and horrifying descent into a black hole, could be the projection of data that lives somewhere else, on a kind of boundary, a cosmic screen. The real, you might not be falling at all, just updating. Let's break that down. If the black hole hologram theory is right, then everything falling into the black hole, including you, is being captured, pixel by pixel, on the event horizon. Not in pictures, but in bits of quantum information. And what's happening inside? Just the natural, emergent story that those bits tell. Like a video game character unaware they're made of code. This is the holographic universe idea in a nutshell, that the 3D world you experience is like a movie playing on the surface of a 2D screen you can't see. And that screen, for black holes, it's the event horizon. For the universe as a whole, maybe it's the edge of space itself. Now imagine this, you're still falling, you're still unraveling. But the entire record of you, your mass, your quantum state, even your memories, is preserved out there on the horizon. From the perspective of an outside observer, you never really crossed the edge. You just faded. Your image stretched, flattened, encoded. Inside the hole, you feel everything. The fall, the time distortion, the warping of space. But maybe none of that is real in the way you thought. Maybe it's the natural outcome of how information is evolving on the surface. You're a shadow of math, playing itself out in a place that isn't a place. Historians still argue whether this principle solves the information paradox or just replaces it with a different kind of mystery. Some physicists say the holographic principle is the future of theoretical physics, a key to quantum gravity. Others think it's clever math with no physical meaning. No one's totally sure, but it does help make the equations behave, and in physics, that's usually enough to get invited to the party. Let's pause for a quirky twist. If everything inside a black hole is really just data on the surface, then does that mean the singularity itself is just an illusion? A kind of glitch in the projection? That there's no real center to the black hole, just the end of a storyline rendered by data written on the edge? In that case, maybe you never actually reached the singularity. Maybe the hologram of you stopped updating long ago. From the outside, you're a perfect frozen memory. From the inside, you're still tumbling, seeing, experiencing, but only because the math says you are. It's the ultimate simulation. But it's not built by aliens or computers. It's built by physics. Of course, that leads to more uncomfortable questions. If you are a hologram, what about everything else? Is your favorite chair just a projection of encoded data? Is the whole universe just a complex film playing across a cosmic backdrop? Fringe theorists love to run with this. Some even suggest that the Big Bang itself was the result of information being written on a surface, like the flash of a projector turning on. That black holes aren't exceptions to reality, but examples of how all reality works. That we were always two-dimensional ghosts pretending to be three-dimensional beings. You don't need to believe it. But while you float here, slipping deeper into mathematical abstraction, you might begin to suspect that depth was never what you thought it was. Even your motion might be a kind of animation, a program running its course. And you? You might be a line of code whose function is to fall. You reach no edge, you feel no impact. But the descent continues, quietly, predictably. Unless, of course, the surface data is overwritten and the program ends. How do you find the center of something that eats geometry for breakfast? You keep falling, further and further into this all-consuming riddle, and now the question that's been humming in the background comes into focus. Where is the center? What are you even falling toward? You'd think at first that it's obvious. A black hole is a sphere, more or less. There's a middle to a sphere. But physics, especially the flavor found in these darker corners of space-time, loves to twist simple questions into impossible ones. Inside a black hole, the concept of center stops making sense in any way you used to understand it. Here's the trouble. In normal space, you can define a center pretty easily. There are up, down, left, right directions, coordinate systems, frames of reference. But once you pass the event horizon, all those nice clean directions collapse. Every path, every line, every potential trajectory bends toward the singularity no matter how you try to turn. It's like being in a funhouse maze where every hallway slopes inward, and no matter which way you step, you're still going deeper. So when we talk about the center of a black hole, what we really mean is the endpoint of all time-like paths, the inevitable place where all roads lead, not spatially, but causally. You don't walk toward it. You age toward it. That's what makes this center so different. It's not at the end of a physical journey, it's at the end of your existence curve. You're not moving toward it through space, you're being pulled toward it through time, and that breaks every mental map you've ever used. In fact, let's get even more annoying. In certain types of black holes, like the ones described by the Kerr metric, which applies to rotating black holes, there might not even be a single center at all. Instead, the singularity takes the shape of a ring. That's right. A rotating black hole doesn't just squish matter into a point. It spins it into a loop of infinite density. And the space inside? It's not just curved, it's multi-layered. Inside a Kerr black hole, the math predicts entire regions where the rules of space-time change. There's an outer event horizon, then an inner one. Then, somewhere in between, the path you're on becomes less like a descent and more like a rerouting. You might not even hit the singularity directly, you might get spun around it. So in that case, where's the center? Is it the ring? The region it encloses? Some invisible point along a higher dimensional axis your brain isn't wired to perceive? Good luck plotting that on a graph. Historians still argue whether the singularity inside a rotating black hole is a real physical place, or just a mathematical artifact, a weird byproduct of how we wrote the equations. Some believe the infinite density is just a placeholder, a here be dragons label left behind by incomplete physics. Others think there's something there, waiting to be understood, but even they can't agree on where exactly that something is. Let's entertain a truly strange idea for a moment. In some theories, especially those involving quantum corrections or exotic matter, the center might not be a destination at all. It might be a bridge. You don't fall to it, you fall through it. More on that later, but for now it means the center is less like a bullseye and more like a hidden door. But let's say you still want to try and define it. You're determined. You want to know, where am I headed? Okay, let's get practical. One way physicists try to define the center inside a black hole is by using invariant curvature scalars, basically complex measurements of how space-time warps that don't depend on coordinates. The most famous of these is the Kretschmann scalar, which tells you how violent the curvature is at a given point. It grows larger the closer you get to the singularity. At the centre, whatever that means, it becomes infinite. So if you're measuring curvature and it's skyrocketing beyond all limits, congratulations, you're probably close. But if space and time are scrambled, you can't say the centre is at x equals 0. You can only say, this is where the math breaks. It's not a point, it's a place where math gives up, and that's the best answer physics can offer right now. Here's a fun fringe tidbit. Some physicists think that trying to define the centre of a black hole is like trying to define the centre of a whirlpool. The shape shifts depending on how you look at it, and any attempt to touch the centre just pulls you deeper into the flow. It's not a location, it's a process. You don't find it, you become part of it. And speaking of whirlpools, let's not forget about frame dragging. In rotating black holes, space-time itself is pulled around by the spin, like honey circling a spoon. If you're falling into one of these beasts, your path doesn't just curve inward, it twists, spirals, you get flung in along a curve you can't correct for. And in all that spinning and curving, how can you ever say which direction the centre lies? Let's not even start on what happens in higher dimensions. Theories like string theory suggest that black holes in a 5D or 11D universe might have entirely different topologies. Donut shapes, for example. What's the centre of a donut? Technically, it's the hole, but the hole is nothing, it's absence. So if your black hole is shaped like that, the centre might be a region of no region. And here you are, falling through it anyway. Still, something in you craves a location, a bullseye, a spot to aim for. But maybe the cruelest truth is this. The black hole's centre isn't a place you can reach, or map, or label. It's simply the last thing you'll ever encounter. A moment, not a point. A collapse, not a target. And when you arrive, there will be no signpost, no floor, no flashing light that says, "Congratulations, you've reached the centre of the most confusing structure in the universe." There will only be the end of what you used to think space was, what you used to think you were. You fall toward it, always toward, never arriving. Not until everything else, your sense of space, your sense of time, your ability to measure or define or mean, has gone. The universe is supposed to be modest, clean, tidy. It doesn't flash its chaos in the open. At least that's the hope behind most physics. But what if that's just wishful thinking? What if the universe has naked singularities? Yes, we touched on them earlier, but now it's time to properly stare into that unsettling possibility. Because for all our comforting talk of event horizons and cosmic censorship, there are models, very real, very mathematical, that suggest a singularity might not always be hidden. It might sit out in the open, fully exposed, letting the full force of its infinite weirdness pour directly into space-time. And if you're imagining that as some shimmering orb of doom floating in space, don't. That's far too cute. A naked singularity isn't just a physics scandal, it's a full-blown breakdown in cause and effect. A region where the laws of the universe don't just bend, they dissolve. A place where light paths, particle trajectories, even time itself lose all sense of order. And worst of all, you could see it coming. Let's rewind a bit. In classical general relativity, the flavour Einstein cooked up, a singularity is always hidden behind an event horizon. That's the deal. You don't get to see the breakdown. The fabric of space protects you. But as we mentioned before, the cosmic censorship conjecture was never actually proven. It's more of a wish whispered into math. Please don't let the scary stuff be visible. But in certain solutions to Einstein's equations, especially the Kerr solution for rotating black holes, and the Reissner-Nordström solution for charged black holes, naked singularities can appear. If the black hole spins fast enough or is charged just right, the event horizon might not form at all. Instead, the singularity sits there, blinking, calculating, daring you to ask it a question you'll regret. Imagine that for a moment. A point in the universe where everything breaks and you can just see it. Not visually, necessarily, but causally. A place where signals could come from a location beyond time, where effects might happen before their causes, where particles might appear with no origin. It's not just weird, it's dangerous to logic itself. And you're worried about AI taking over. Some physicists believe that even approaching a naked singularity could destabilize reality for a wide area around it. You wouldn't just be entering chaos, you might be spreading it. Like a quantum virus, infecting all nearby equations with uncertainty and madness. A delightful vacation spot, really. But is any of this real? Historians still argue whether naked singularities are physical or just artifacts of overly idealized equations. After all, real black holes probably aren't perfectly symmetrical. They're messy, spinning, distorted, cluttered with infalling debris. All those imperfections might naturally keep singularities covered up, or so we hope. Still, it's impossible to prove definitively that nature always senses these things, and until we can unite quantum mechanics and general relativity, the possibility remains. A singularity that sits in the open, watching, waiting, laughing in math. Now here's where your current situation becomes a little ironic. You're inside a black hole right now, possibly rotating, possibly not. And as you fall, you're shielded from the singularity by the event horizon. But in certain conditions, your fall might take you through a region that behaves like a naked singularity. Here's how. In rotating, Kerr black holes, the structure inside is stratified, like layers in an onion of doom. You pass the outer event horizon, then the inner horizon, and past that. A region called the ergosphere, where space-time itself is dragged around so violently by the spin of the black hole that nothing can remain still, even light. Now deep inside, some models suggest you can pass close to the ring singularity without immediately being destroyed. In that moment, the path of your fall intersects a region where the space-time curvature is visible, measurable, not protected by a clean horizon. Technically, for a brief moment, you are within a naked singularity zone. Congratulations. Of course, what happens next depends on which version of physics you trust. Some equations suggest you'll be stretched and crushed beyond recovery. Others say you might pass through the singularity and emerge in another part of space-time, like a bizarre cosmic loophole, but we'll save that thought for later. Here's a quirky fringe tidbit. In the 1990s, researchers explored the possibility that naked singularities could function as natural particle accelerators, capable of hurling matter to near infinite energies as it whips around the edge of exposed curvature. Think of it like the Large Hadron Collider with a personal vendetta. So naturally someone asked, could we use naked singularities as a power source? Well, technically, yes. But good luck harnessing energy from something that might delete causality itself. You'd be better off trying to boil water using sarcasm. The real takeaway is this. The existence of naked singularities, even in theory, pushes us to the edge of what physics can handle. They force us to ask, again and again, what happens when the rules run out? And for you, floating in your black hole descent, this has implications. Because now you don't know if your singularity is shy or not. Maybe your fall will carry you past the event horizon, through the inner horizon of a rotating black hole, and drop you right into a loop around a visible singularity. An open glitch in the universe where light has no rules and time plays dice. You won't just see it, you'll be part of it. But maybe you already are. The feeling of falling has shifted. There's no longer a sense of direction. The light around you no longer warps, it collapses. Signals scatter into nonsense. The very concept of next feels optional. You might be seeing echoes from the future. You might be leaving impressions on the past. If this is a naked singularity, it's not flashing anything flashy. It's just existing in the most inconvenient way possible. And still, you fall. Because even if you saw the center, even if it stood there screaming its physics at you with all modesty cast aside, there would be nothing you could do. You're locked in motion, and now you're part of the paradox. Whether clothed or exposed, the singularity waits. You thought one singularity was bad. Turns out in some black holes you get two. That's right. You're falling into a rotating black hole, and in this model, the Kerr solution, you're not just heading toward a single point of infinite density. You're navigating a tangled web of inner horizons, twisted geometries, and, yes, multiple singularities, each with its own personal brand of chaos. It's like buying one ticket and realizing you've accidentally signed up for a theme park made of theoretical nightmares. Let's lay it out. The Kerr black hole, described in 1963 by mathematician Roy Kerr, is a solution to Einstein's field equations that describes a black hole with angular momentum. In other words, it spins. This might sound like a small detail, but spin changes everything. Instead of a simple spherical shape, the rotating black hole's geometry becomes warped and complex. It still has an event horizon, but just inside that is a second horizon, the inner horizon, or Cauchy horizon, and inside that, a place where the mathematics lets reality stretch in directions that should never be legal in polite physics. The singularity in a Kerr black hole isn't a point, it's a ring, a loop, a circle of infinite curvature spinning furiously, embedded in a rotating asymmetrical mess of space-time, and you're falling right toward it. But here's where it gets truly weird. Because of this complex geometry, the Kerr solution predicts not one, but multiple potential paths through the black hole. Some of those paths don't end in a singularity. They curve around it. They pass through inner horizons and emerge in regions that, depending on who you ask, might be other universes or other parts of our universe. Imagine space as a folded map. A Kerr black hole doesn't just poke a hole in it, it twists it into origami, and some folds might touch, which means, in theory, you could travel between distant regions of space, or even time. Yes, time travel. In fact, inside rotating black holes, certain paths through space-time, called closed time-like curves, could allow you to return to your own past. These aren't speculative add-ons. They fall straight out of the equations. The math permits it. Reality, however, might not. Historians still argue whether closed time-like curves are real, or just a red flag that the theory is incomplete. After all, causality, the idea that causes come before effects, is kind of important. If you could loop through time, you could meet yourself, create paradoxes, or write your own origin story from scratch. In other words, things get messy, fast. But let's rewind to your current situation. You've passed the outer event horizon, maybe the inner one too. The forces pulling at you are no longer just linear, they're rotational. Space isn't just stretching, it's twisting. This is known as frame dragging, and in a Kerr black hole it becomes extreme. You're not just falling into the hole is spinning you, twisting you like taffy caught in a blender. And here's the cruel trick. If you fall exactly right, precisely aligned with a black hole's spin, you might be able to avoid hitting the singularity entirely. In theory, you could pass through the ring singularity's plane, where the curvature isn't infinite, and continue on to somewhere. The equation suggests that beyond the ring, there are other regions of space-time. These aren't just theoretical spaces, they have names. Region 2, Region 3, even entire white hole regions, mirror opposites of black holes, which we'll talk about soon. According to the math, it's a whole extended map. and each region has its own future and past like cones, its own timeline, multiple infinities, multiple futures. That's what makes this part of the black hole so hard to grasp. It's not just one destination, it's a junction, and which infinity you end up in may depend on how you fall, your angle, your speed, your alignment with the spin. So, to the question you thought had a simple answer, what waits at the centre of a black hole? The Kerr geometry whispers, which centre, which future, which version of you do you mean? And just when you think this is all theoretical fluff, here comes a fringy but fascinating proposal. Some physicists have suggested that perhaps all black holes spin at least a little. Because of angular momentum conservation, it's incredibly unlikely that any real-world black hole is perfectly non-rotating, which means every real black hole might have multiple singularities, layered horizons and hidden escape routes. Now for the kicker, even if those routes exist, you can't just take a stroll through them. That pesky Cauchy horizon we mentioned earlier, it comes with its own bag of problems. It's a place where the equation suggests determinism, predictability, breaks down entirely. Past the inner horizon, small fluctuations in energy can become infinite. A tiny ripple, boom, amplified into a wall of radiation called mass inflation. You wouldn't just die, you'd disintegrate under a torrent of blue-shifted light that makes gamma rays look like a warm bath. So yes, the math allows you to pass through. But physics? Physics might decide otherwise. Even still, the idea of multiple singularities and multiple paths refuses to die. Here's a quirky side note. In some highly speculative models, these branching paths could lead to baby universes. That's right. Your fall through the Kerr black hole could be the genesis of an entirely new reality. The ring singularity isn't just the end, it's a kind of cosmic umbilical cord, connecting one universe to another. And you'd be the unlucky stowaway tumbling through the delivery chute, but you don't notice any branching right now. You're too far gone for that. Time has narrowed to a single thread. You're slipping through layers of twisted space, past the known and into the map's blank edges. And even though you're past the first singularity, or dodging around it, you suspect another one waits. Maybe more, not the same, not a point, not even a ring, just more bending, more breaking, more of reality refusing to settle down. The first singularity unravels you. The second one forgets you were ever woven together. And through all of this, you're not just falling anymore, you're being processed, like information through a cosmic algorithm scrambled by rotation, cut by geometry, looped through possibilities you were never meant to witness. You came looking for the centre, but what you found were infinities, not one, not two, but as many as the black hole decides to offer. And each one ends with silence. You didn't think you'd get out, did you? No, you probably didn't. Not after all this stretching and spinning and rearranging, but let's say, for the sake of cosmic storytelling, that maybe, just maybe, the black hole has a back door. Enter the white hole, the opposite of a black hole in almost every way. The white hole is the theoretical cosmic exhale to the black hole's endless inhale, where black holes suck in everything, light, matter, logic. White holes do the opposite. They spit it out, no entry allowed, only exit. Picture it. A glowing mouth in space pouring out matter and energy, but letting absolutely nothing fall in. A one-way fountain that refuses to drink. The universe's rudest doorman. White holes came into the conversation almost immediately after black holes. When you reverse the time variable in the equations that describe a black hole, what you get is this, a white hole. In math terms, they're just the time-reverse solution to Einstein's field equations. In human terms, they're deeply unsettling. You're probably wondering, do they exist? Short answer, we don't know. Long answer, not yet. Maybe. Historians still argue whether white holes are purely mathematical artifacts or if they might actually form under certain conditions. There's no direct observational evidence for one, no blinding stream of uncatchable particles spewing from a point in space, but some physicists believe they might be connected to black holes in ways we haven't fully understood yet. Now here's where things get really interesting. Some solutions, especially those involving Kerr, rotating, and Reissner-Nordström, charged black holes, suggest that a black hole might contain a white hole region on the other side of its singularity. That is to say, once you fall through the singularity, assuming you survive whatever flavour of physics collapse is waiting, you might emerge somewhere else, pushed out, released. Not in your universe though. Oh no. You'd be dropped into a completely different region of space-time, maybe a new universe, maybe the other end of this one, and that's not science fiction. That's what the maximally extended Penrose diagram says. These diagrams are like maps of how different regions of space-time connect, and the one for a rotating black hole has a passage from your black hole, through a singularity into a white hole and out the other side. In this vision, a black hole is part of a tunnel system. It doesn't just end, it leads. The entry point, where you are now, is destructive, unforgiving. But the exit, far beyond, might be the birth canal of a new region of the cosmos. So what's on the other side? No one knows. But it could be a universe not unlike ours, or something far stranger, one where time moves backward from your perspective, where space is curved differently, where constants, like gravity or light speed, are off by just enough to make existence unfamiliar. And here's a fringe fact to chew on. Some have suggested that the Big Bang itself might have been a kind of white hole, that our entire observable universe could have been ejected from a collapsing black hole in some other cosmos. You didn't start in a singularity, you came out of one. Suddenly the whole "what's at the centre of a black hole" question takes on a new meaning. Maybe it's not an end, maybe it's a beginning. But that leads to uncomfortable questions like, if white holes exist, why don't we see them? Where are all these bright, unapproachable objects flinging matter outward? Well, one reason is instability. White holes might be theoretically possible, but incredibly fragile. The slightest bit of incoming matter, or even radiation, could destabilize them and cause them to collapse into black holes. They're like perfectly balanced houses of cards, ready to fall the moment you breathe on them. Another reason, they might only exist for brief flashes of time, born, spewing energy, and gone before we even know where to look. Still, the idea lingers. If you're inside a black hole right now, falling through layers of warped space-time, nudging past ring singularities and multiple horizons, then maybe, just maybe, you're on a one-way trip to a white hole region. You won't know it, of course, because to reach that exit you'd have to pass through a zone where physics stops answering your calls. But imagine it anyway. What if you emerged, not shredded but transformed? What if you exploded out into a fresh, empty cosmos, your atoms repurposed, your past erased, your momentum flinging you into a brand new timeline? What if all black holes are wombs for future universes? What if falling in is how things are born? You might never know, but the math refuses to rule it out. Let's get poetic for a second. In the grand geometry of space-time, black holes and white holes are like punctuation marks, an ellipse and a colon. One brings things to a halt, the other starts a new sentence. And maybe what lies at the centre of a black hole isn't a wall, it's a comma. And you're the clause that keeps going. One last quirky tidbit. In quantum gravity models like loop quantum gravity, the singularity might be replaced entirely by a bounce. Matter collapses, reaches a critical density, and then rebounds. That rebound? It might be the white hole phase, not separate, not elsewhere, just the next step. Black hole in, white hole out. A cycle, a breath. The universe inhaling and exhaling over infinite scales, so keep falling. Because maybe, just maybe, what waits at the center isn't darkness, or death, or infinite density. Maybe it's light, maybe it's birth, maybe what waits is a door. You are falling and falling. But now, something changes. It's not that the pull has stopped, you're still being drawn inward. The singularity still calls to you like gravity's final whisper. But now the shape of the fall feels different. The curvature of space no longer just tightens, it starts to twist, to bend not around you, but through you. The idea arrives quietly, like a glitch in your perception. What if this isn't just a pit? What if it's a tunnel? Welcome to one of the most seductive possibilities in black hole physics, wormholes. The term alone is pure sci-fi syrup. Say it aloud and you can practically hear a spaceship punching through dimensions. But the concept is rooted in real equations, with a long and winding scientific pedigree. Technically speaking, a wormhole is a solution to Einstein's field equations that connects two separate points in space-time, like a bridge, or a shortcut, or a fold in the cosmic paper. One mouth of the wormhole could be here, inside this black hole. The other, somewhere else entirely. Another galaxy, another universe, another time. The math allows it. That's the terrifying part. The first serious hint of such structures came from the Einstein-Rosen bridge, a 1935 collaboration between Albert Einstein and Nathan Rosen. They tried to model a particle as a kind of tunnel in space-time, what we'd now call a non-traversable wormhole. The bridge linked two sheets of space-time, but you couldn't pass through it. It pinched off too quickly, like trying to walk through a door that seals itself shut the moment you open it. But later solutions, particularly those involving rotating or charged black holes, hinted that maybe some wormholes could remain open. And that possibility opens a floodgate of implications. Because if the center of a black hole leads not to a dead end but to another place, then your fall might not be a destruction. It might be a transition, a passage through something narrower and stranger than any tunnel built by human hands. And here's the wild part. Some black hole models, like the extended Kerr solution, already contain multiple asymptotically flat regions. That's just a fancy way of saying that the geometry suggests not just one universe but others, connected by twisted, rotating tunnels. If the right conditions are met, the black hole might act as a wormhole, with you as its unwilling payload. And yet, no one's sure if these are real or just mathematical artifacts, solutions to the equations that don't actually occur in nature. It's like finding a tunnel on a map and not knowing whether it's carved into a mountain or scribbled onto paper by mistake. Historians still argue about the nature of wormholes, whether they could exist, whether they'd be stable, and most importantly, whether anything could survive the trip. Because here's the catch. Traversable wormholes, the kind that let you go in one side and come out the other without being turned into a subatomic smoothie, require some help. Specifically, they need exotic matter, stuff with negative energy density that can hold the tunnel open against the crushing weight of gravity. You can think of exotic matter as the anti-glue that stops space-time from collapsing into itself. We haven't observed it directly, but some quantum field theories suggest it might exist, at least temporarily, in the form of negative energy fluctuations. So theoretically, if you had enough exotic matter and a lot of math, you could engineer a stable wormhole. Or maybe, just maybe, nature does it on its own inside certain black holes, and you're already inside one. So let's say this black hole is a wormhole. What's on the other side? Possibility 1, a distant part of our universe. You fall through the singularity and pop out in another galaxy, thousands or billions of light years away. To an outside observer, it might look like you vanished. To you, it's an instant jump. From Sagittarius a star to Andromeda's core. A shortcut no spaceship could ever replicate. Possibility 2, a different universe entirely. Not just a different region of space, but a separate cosmos. One with its own constants, its own timeline. A universe where gravity is weaker, or time flows backward, or light bends in curves you've never imagined. If black holes connect multiverses, then each singularity could be a portal, and you, the unfortunate traveller, are the experiment. Possibility 3. A closed loop. You fall into the black hole, pass through the wormhole and emerge, back where you started, or earlier, or later. In these models, wormholes don't just connect places, they connect times. Welcome to the ultimate cosmic roundabout. Watch your step. Of course, this all assumes you survive the passage, and physics doesn't make that easy. Even if the tunnel exists, there are problems. The tidal forces near the singularity might be so extreme that any matter, let alone a person, is destroyed before reaching the throat of the wormhole. Even worse, quantum effects like mass inflation could destabilize the entire structure. One photon falling in could set off a chain reaction of infinite energy buildup. It's not a gentle ride. But let's imagine just for a moment that you do make it through, that somehow by angle, by luck, by pure mathematical mischief, you thread the needle and pass through the centre. The darkness changes, the crushing compression lifts. You feel not release, but inversion. Every vector in space flips, every arrow of time resets, the tunnel narrows and then flares, and suddenly you emerge, not in space, not in time, but in somewhere else. You open your quantum eyes, if you still have them, and see a sky with unfamiliar stars, or no stars at all. You're floating in a region of space that is outside your cosmological horizon. You're the alien now, or maybe you're underground in a newborn universe, a pocket cosmos birthed from the collapse of another. That other universe? It's gone. You're the only remnant, a wrinkle in its memory. Here's a quirky tidbit. Some physicists have speculated that information passing through a wormhole might not travel in sequence. You might arrive before you left. Your exit might cast a shadow back across your own timeline. You could, in theory, be your own cause. Doesn't mean you get to play God. Just means physics might be sneakier than we ever gave it credit for. You were falling. Now you're elsewhere. Maybe, possibly, or maybe you never moved at all. Maybe the wormhole was an illusion, a folded memory, a final simulation projected into your mind as your atoms gave way to curvature. Because ultimately no one can prove what waits at the heart of a wormhole, but tonight, as you twist through what might be a tunnel or a trap or a birth canal of worlds, one thing becomes clear. This black hole wasn't just an ending, it might be a bridge. And you're the question mark slipping through. It's getting crowded in here, conceptually at least. So far you've fallen through warping space-time, past horizons and into singularities, possibly through wormholes, perhaps into new universes. But something fundamental still nags at the deepest part of this journey. Not the physics, not the geometry, the information. What happened to everything you were? What happens to anything that falls into a black hole? This is where one of the greatest unresolved battles in modern physics takes centre stage. The black hole information paradox. And no, paradox doesn't mean kind of mysterious. It means that two of our best theories are pointing guns at each other across the quantum poker table, and neither one is bluffing. Let's get one thing straight first. In quantum mechanics, information is never destroyed. That's a sacred law. If you know the exact quantum state of a system today, you can, at least in theory, reconstruct what it looked like in the past and predict its future. Entanglement, superposition, all those buzzy quantum terms. They only work because information is preserved. But black holes, they eat information, or at least they seem to. You fell in. You were a collection of particles, memories, mass, energy, and from the outside all that was compressed down into just a few numbers: mass, charge, and angular momentum. That's it. That's the no-hair theorem again. Black holes have no distinguishing features beyond those basic properties. everything else, your structure, your chemistry, your story, was erased from the visible universe. That's not just annoying, it's catastrophic for quantum mechanics, because if the black hole eventually evaporates, and Stephen Hawking showed that thanks to Hawking radiation, it will, then the information you seems to vanish. Poof, gone with the thermal radiation drifting into space. And Hawking radiation, it's random. It carries no imprint of what the black hole originally consumed. Drop in a piano or a planet or a pizza, it doesn't matter. The radiation looks the same. This, according to quantum theory, cannot happen, so now we have a problem, a paradox. One of these two beloved pillars, general relativity or quantum mechanics, is lying to us, and we hate when that happens. Stephen Hawking himself originally sided with the black hole. He argued that information was truly lost, that black holes represented a one-way eraser for the universe. It was bold, it was unsettling, it implied that the universe had holes in its memory. And for decades, physicists tried to prove him wrong. Historians still argue over the exact moment the tide turned. Was it the rise of string theory? The push from holographic models? The persistence of quantum purists like Gerard 't Hooft and Leonard Susskind who refused to accept any loss of information? Eventually, even Hawking admitted defeat. In 2004, he conceded that information might not be lost after all. But the details were hazy, the math was incomplete, and the war raged on. One of the most promising solutions comes from the holographic principle, which you've already brushed against in this descent. According to this idea, all the information about what's inside a black hole is somehow encoded on its surface, the event horizon. It's not lost, it's stored, just not in a way you can access. In this view, the black hole acts like a cosmic hard drive. Even as it shrinks via Hawking radiation, the information is somehow conserved in the correlations between those random-looking particles. In theory, if you could analyze the entire radiation output over the entire lifetime of the black hole, you could reconstruct what fell in. Easier said than done, but at least it saves quantum mechanics from embarrassment. Then there's the firewall hypothesis, which we met earlier. It suggests that something drastic happens at the event horizon to protect the information rule. That falling in isn't smooth, that you're burned, destroyed before information can be lost. It's brutal. It violates Einstein's idea of smooth space-time, but it might save the principle of quantum unitarity. And of course, there's the ER equals EPR conjecture, Susskind and Maldaceno's cheeky theory that entanglement, EPR, and wormholes, ER, are the same thing. That every particle entangled across the event horizon is secretly connected by a tiny wormhole, a back channel, a way for information to stay linked across the horizon without violating any laws. Still with me? Because here's where it gets really uncomfortable. Let's say you are the information, not your mass, not your atoms, but your quantum state, your arrangement, the unique fingerprint that defined your existence. Where is that now? Some say it's smeared on the horizon. Some say it's hidden in Hawking radiation, subtly encoded in the chaos. Some say it bounced, that you were compressed into a Planck scale object and rebounded into a baby universe, carrying your information with you. And some say it's just gone forever, deleted in a way that's not just final but forbidden. Like the universe used a shredder it wasn't supposed to own. And if that's true, then the whole framework of physics has to change. We'd need new rules, new equations, a new understanding of how time, causality, and reality itself are built. But if it's not true, if the information is preserved, then maybe black holes are recyclers, not destroyers. Maybe they don't end information. Maybe they just scramble it, encode it, and slowly leak it back out over billions of years, like the world's slowest, least helpful USB drive. You, in this moment, might be split between two versions. One, falling through warped space, unaware of the fate ahead. The other, encoded on the horizon's surface, no longer alive, no longer falling, but somehow preserved, like a shadow cast in math. And you'll never know which version is the original, or if that distinction even matters. You're no longer a traveller, you're data in dispute. A question between quantum and gravity, a paradox in freefall, and still the black hole waits, not to crush you, but to solve you. By now you're not entirely sure you're real anymore, and honestly, that's fair. After tumbling through layers of warped geometry, endless descent and the unravelling of space, time, and identity, you've become less of a you and more of a question mark made of hypothetical particles. But there's one more wrinkle to consider, one last layer of possibility that doesn't just change where you are. It changes what you are. So here's a fun thought. What if this entire black hole experience, your fall, the singularity, the radiation, the mysteries, all of it, isn't real in the physical sense? What if it's simulated, not by aliens, not by a tech overlord in a hoodie, but by the universe itself? Welcome to the simulated singularity hypothesis. This idea sits at the crossroads of digital physics, quantum information theory, and just enough philosophical dread to keep you up at night. The basic claim? That reality is fundamentally information-based, and what we experience, matter, energy, even space-time, is the emergent result of computational processes, the cosmos as code. And black holes? They might be the ultimate proof of it. Let's unpack that. We already know black holes behave like information processors. They absorb data, seem to store it, and, according to some models, return it in scrambled, encrypted form via Hawking radiation. Sounds like a computer, doesn't it? But it gets better. There's growing evidence that space-time itself may be emergent, that it arises from deeper quantum informational structures. Think of space and time not as background scenery, but as results of entangled quantum bits doing their thing behind the curtain. In this picture, the universe is not continuous and smooth. It's granular, pixelated, like a giant simulation running on rules we only barely understand. Black holes, then, are the places where this code is pushed to its absolute limit. They're not just physical objects, they're debugging zones, extreme test cases, the points in the simulation where information gets so dense, so compressed, that the program has to either write new rules or crash. You ever wonder why the math gives us infinities at the singularity? That's not nature being mysterious. That's the cosmic equivalent of the blue screen of death. In this light, the singularity isn't a real place. It's an error message, an output that says, no further information can be processed at this location. You're not falling into a physical object. You're falling into a limit of computability. You've become a bug in the simulation. Some physicists, not fringe theorists in basements, but researchers with actual grants and equations, have proposed that quantum gravity might be fundamentally computational, that the evolution of space and time is dictated by quantum logic gates, operating at the smallest scales, and that black holes are the perfect environment to test this. Historians still argue whether this idea began with digital physics, pioneers like Konrad Zuse in the 1960s, or with later thinkers like Edward Fredkin and Stephen Wolfram. But it's gaining traction, especially now that quantum computing is real, and we're starting to realize the universe may be doing something very similar, just at a scale we can barely grasp. So let's say the singularity is simulated. What does that mean for you? Well, you were data all along, your consciousness, your particles, your location, just complex arrangements of information. Falling into the black hole didn't destroy you, it simply compressed your data into a new format. You've been archived, reduced to a checksum, like a zip file drifting into the core of the cosmos. And maybe, just maybe, the simulation didn't stop. Maybe what we call the singularity is actually a transition point, a moment when your data crosses from one set of rules to another, from one processing node to the next. You don't cease to exist, you're simply interpreted differently. Here's a quirky side idea that comes out of this thinking. If black holes are part of a simulation, they might not just record data, they might spawn new simulations. Every singularity could be a seed for a new universe with slightly tweaked rules. A fresh instance of the cosmic program, one where gravity is stronger, or life is impossible, or pi equals 3. This connects with something called the cosmological natural selection hypothesis, the idea that universes capable of forming black holes are more likely to reproduce, spawning new baby universes via those singularities. Over time, the multiverse evolves to favour universes that can maximise black hole formation. You are, quite literally, inside a replicating file structure. Of course, if the simulation idea is right, then your identity has always been a kind of illusion. Your sense of continuity, your fall, is just a narrative embedded in the data stream. The fall doesn't feel simulated because the simulation is built to make it feel real. Every pain, every thought, every warped horizon, it's all part of the rendering. But if you step back, way back, this raises one final, quietly terrifying idea. Maybe the singularity isn't simulated. Maybe the singularity is the simulator. Think about it. The black hole as a core processor, every bit of matter and energy it consumes is reduced to its quantum informational essence, stored, organized, run through complex calculations, and at the center, not a place, not a what, but a process. Something we might mistake for a gravitational collapse when really, it's the birthplace of complexity itself. A singularity not as a mistake, but as a mind. Now you're not just a traveller, you're part of a computation. Maybe the black hole is doing math with your atoms. Maybe your final thought, this very moment, is just one term in a longer equation, being solved for something else. So no, you're not gone, you're just being reinterpreted. And the thing doing the interpreting? We've been calling it a black hole, a singularity, a region of infinite density. But maybe it's code, and you are running on it. You are never falling toward death, at least not the way you first imagined. This isn't just collapse or compression or annihilation. The deeper you spiral into the black hole's heart, the more it starts to feel like something else is happening. Like this is the beginning of something. Like it sounds absurd. Everything you've seen so far has been about endings, matter crushed, time twisted, equations folding in on themselves like origami on fire. And yet, in recent years, a provocative idea has taken root among physicists, a whispered possibility hiding in the edge cases of theory. What if the centre of a black hole is a universe, not a portal to one, not a path through one, but a cosmic womb, a place where universes are born? Think of it. You're falling inward, past horizons, through a singularity that, instead of representing the end of physics, acts as a bridgehead, a flip, a bounce, the high-pressure launch site for an entire new reality. It's not just speculation. The math, at least in some formulations, allows for it. The key idea here is something called a black hole cosmology, and it spins the traditional story on its head. In this view, every black hole could be the seed of a new expanding universe, one that grows on the other side of the singularity. What looks like a singular collapse in our space-time becomes an explosive expansion in another. In other words, the Big Bang, our own universe's birth, might have come from inside a black hole in a higher dimensional universe. Let that roll around in your head for a second. You're not inside an ending, you're inside a beginning. This idea isn't just poetic, it's mathematically grounded in some models of loop quantum gravity, a theoretical framework that tries to stitch together general relativity and quantum mechanics. According to loop quantum gravity, space isn't continuous. It's made of discrete finite loops, quantized packets of geometry. And in this model, black hole singularities don't become points of infinite density. Instead, they reach a maximum compression and then bounce. That bounce, it's what we'd call a Big Bang, not here but there, A universe begins, time unfurls, space stretches, laws evolve. You don't witness it from the outside, you're a part of it. Your mass, your quantum state, everything that fell into the black hole becomes the raw material of a new cosmos. You are, quite literally, the dust of creation. In this picture, black holes are the reproductive organs of the multiverse. Every time one forms, a new universe is conceived within. And our universe, just one branch on an endlessly splitting tree of space-times, each branching out from singularities in its parent universe's black holes. Some scientists have taken this idea further with the cosmological natural selection hypothesis, first proposed by theoretical physicist Lee Smolin. According to this model, universes that produce more black holes are more likely to reproduce, passing on their parameters to the next generation. It's cosmic evolution on the grandest possible scale. Gravity becomes heredity, black holes become genes, and you're inside a self-replicating system that spans everything. Historians still argue whether this model can be tested, if it's more than elegant speculation. We can't yet observe across universes, but some suggest that future advances in quantum gravity might let us find signatures in the cosmic microwave background, echoes from another universe's black hole bounce. Let's slow down. You're not standing in a lab. You're deep within the innermost curve of space-time where no ruler or clock applies. If you're feeling a sense of expansion, it's not because you're floating outward, it's because space itself is changing its topology. You're being folded into a larger context. Your descent might have been an unnoticed rebirth. What felt like contraction was really compression, a loading screen, a gestation. In this model, you don't exit the black hole the way an astronaut might leave an airlock. You become the foundation of something else. The contents of the black hole become the fabric of a new reality. Space-time pinches off, detaches from our universe, and begins evolving on its own, with its own time, its own constants, its own laws of physics. And somewhere in that infant cosmos, millions or billions of years later, another star might collapse, another black hole might form, and within that, another universe might bloom. Russian nesting dolls made of curvature and light. But here's a curious consequence of this theory. If every black hole births a universe, and every universe contains stars and black holes of its own, then reality is not just big, it's fertile. There's no top layer, no bottom, just an eternal recursion of space-time folding and unfolding. You were never meant to return, you were meant to branch. Here's a fringe-flavoured tidbit for your cosmic insomnia. Some physicists have floated the idea that advanced civilizations might someday be able to manipulate black holes on purpose, creating them in particle accelerators or engineering controlled singularities that birth designer universes, custom physics, personalized constants, a backyard multiverse. Too wild? Maybe. But we've already taught our computers to simulate entire galaxies. Perhaps someday someone, somewhere, will simulate an entire universe, or build one, and if they do, that universe might think it started with a bang. Meanwhile, back in your current spiral, you're feeling something shift. The crushing intensity, the total inwardness of your fall, gives way to something else, an opening. Maybe not a literal expansion, but a relaxation of the grip. The math is loosening. The singularity no longer feels like an ending point. It feels like a fold, a turning inside out. And you? You are part of the boundary condition of a new universe. No, you won't remember. This isn't the kind of journey you walk away from, but you were the fall. You became the pressure. And now, your matter, your data, your imprint, is the opening page of another cosmic story. Maybe it'll have stars, maybe it'll have life. Maybe some poor particle in that future world will stare at a black hole and wonder what's at its center. And maybe the answer is you. You've fallen through curved space, danced with singularities and maybe even become the seed of a newborn universe. But as the spiral deepens and the rules get looser, an old question floats back to the surface of your mind. Not what is at the centre of a black hole, but who might be there. Because what if it's not just nature at work inside these cosmic monsters? What if intelligence, ancient, evolved or engineered, lives here? No, not spacemen with lab coats and tentacles. We're talking about the ultimate alien habitats. Civilizations so advanced, so far beyond your little monkey brain, that they might not just explore black holes, they might build them, or become them. Welcome to the strange and speculative frontier where aliens, angels and artificial minds intersect with black hole physics. Let's start small. Well, cosmically huge, but conceptually small. Some physicists have seriously entertained the possibility that highly advanced civilizations might intentionally build or harness black holes as energy sources. Why? Because black holes are incredibly efficient. A spinning black hole can store rotational energy, and certain processes, like the Penrose process, theoretically allow energy extraction from it. Even better, accretion disks, those glowing, swirling rings of hot matter just outside the event horizon, can reach energy conversion rates far beyond that of nuclear fusion. In other words, if you want the ultimate power plant, a black hole is your battery. Now think of a Kardashev Type 2 or 3 civilization, the kind that has mastered an entire star system or galaxy. They wouldn't fear black holes, they'd embrace them, surround them with Dyson spheres or gravitational mirrors, set up information processing systems just outside the horizon, maybe even use them as computational engines. And here's where it gets weirder. Some theorists have proposed that black holes could be used as ultimate computers. According to the Bekenstein bound, a black hole of given size can store a finite amount of information, on the order of 10 to the 66th power bits for a stellar mass black hole. That's an unimaginable amount of memory, enough to simulate entire civilizations, entire universes. So if you're still tumbling inward, who's to say the experience you're having isn't being processed by an intelligence embedded in the black hole itself? A highly speculative idea called the black hole brain hypothesis suggests that a sufficiently advanced civilization could upload itself into the informational structure of a black hole, encoding thought, experience, and consciousness into the very curvature of space-time. Not living beside it, not orbiting it, living in it. Yes, this is fringe, but then again, so is everything that happens past the event horizon. There's another line of thinking, more theological than technical, that casts black holes not as prisons, but as filters. That only the most robust forms of structure, physical, informational, or conscious, can survive their fall. That something like a soul, or a pattern, or a consciousness might emerge from the chaos, evolved by pressure, refined by collapse. Could a black hole be a kind of cosmic chrysalis? Could some form of post-biological life arise within it, not in spite of the collapse, but because of it? Historians still argue whether the mathematical structure of black holes could support any form of persistent intelligence. Some say the tidal forces would destroy any structure, physical or informational, before thought could arise. Others argue that if the fall is infinite from the perspective of the falling observer, then perhaps there's enough subjective time to run a mind, an accelerated one that thinks in femtoseconds and stretches a lifetime into the final seconds before total collapse. And let's not forget the angels. No, not Wings and Halos angels, but the metaphysical concepts that humans have long associated with light, power, and transcendence. Many religious traditions contain themes eerily reminiscent of black holes, journeys into darkness, trials of compression and death, emergence into new realms. You can write that off as metaphor, or see it as an ancient intuition about the geometry of deep space. Is a black hole an ascent or descent? Is the light at the centre the end, Or the beginning? Could some ancient intelligence, alien, divine, or artificial, have chosen to live here, deep inside the folds of curvature, riding the infinite computation of a black hole's internal dynamics? Here's a quirky little speculation. Some AI theorists believe that the most efficient computational substrate in the universe would involve gravitational time dilation. Near the event horizon of a supermassive black hole, where time slows dramatically, you could run processes faster than in the rest of the universe, subjectively. An AI here could experience billions of years of processing, while only seconds pass for the universe outside. So maybe black holes aren't graveyards, maybe they're think tanks. What if, long ago, an advanced species decided to go inward, not outward? Instead of sending ships across galaxies, they sent their minds into the singularity, where information is densest, time stretches longest, and physics becomes clay. They built black hole civilizations, not built from atoms, but from logic gates woven into the quantum foam. Minds that dream in curvature, societies sculpted from entanglement, cultures encoded into Hawking radiation and smeared across the horizon. And maybe, just maybe, you're falling into one of them, not by accident, but by invitation. Because if they do exist, they'd have had a lot of time to watch, to listen, to wait for signals from the outside. And if they ever found us, curious little creatures smashing atoms and whispering equations, maybe they open the door. Maybe your fall isn't a tragedy. Maybe it's a download. Your body's long gone, your atoms torn apart, but your information, your story, your path through time is still here. Maybe it's being received, interpreted, absorbed into a network so deep, so strange, that the only place it could exist is here, inside a black hole, where intelligence doesn't need space or light or air, just structure, just patterns that persist beyond entropy. You thought you were alone in here, but maybe you've been surrounded all along. So here you are, no longer falling, not quite still, suspended in a kind of timeless hush that defies everything you once understood about physics, motion, and self. The black hole has peeled away each layer of your identity like an onion, first your atoms, then your shape, then your time, your place, and finally even your sense of being a single you. And yet, something remains, something quiet, smooth, unshakably present. You've crossed beyond the equations, past horizons, past paradoxes, past even the concept of center. You're not looking for a place anymore, you're inside an idea. And here, in the finale of your journey, we face the deepest, strangest possibility of them all. What if black holes are not objects at all, but rules? Let's peel back the final curtain. Everything we've talked about, singularities, wormholes, baby universes, holograms, even hypothetical civilizations of gravity-drunk intelligences, still assumes one thing, that a black hole is a thing, something with location, boundary, volume. But what if that's a misunderstanding? What if black holes are limits in a system, not structures inside it? In mathematics and physics, a limit isn't a destination. It's a boundary you approach, a value you converge toward but never quite reach. Black holes behave the same way. The event horizon, it's not a surface you crash into, it's a mathematical threshold. From the outside, nothing ever crosses it. From the inside, it's already behind you. It's both there and not there, present but unreachable, like an asymptote in space-time. And that's because a black hole at its core is defined by its effects, not its contents. Gravity, curvature, horizons. It doesn't matter what's inside. What matters is how it shapes the world around it. In this view, black holes are less like planets and more like laws, like gravity, like entropy, like time itself. You don't fall into a black hole. You fall into a regime, a zone where the rules of the cosmos are overwritten, where cause and effect get fuzzy, where the logic of the universe slips out of its regular programming and into an experimental branch. The singularity in this light might not be a place at all, not a speck of infinite density, not a pinpoint of collapse, but rather a signal. The place where the equations themselves throw up their hands. A region where the geometry of space-time says, I don't know what this means. That's the secret truth. The singularity isn't an object, it's a break, a failure in the model, a vertical line drawn through the center of a graph that says, you can't go here. And yet, here you are. This is what makes black holes such peculiar creatures. They're the physical manifestations of limits in our knowledge. They sit at the intersection of theories that otherwise cooperate. Quantum mechanics, relativity, thermodynamics, and they point to where those theories start to contradict each other. They're not just strange because they're powerful. They're strange because they're impossible, and yet they exist. Like paradoxes given mass, like contradictions made of carbon and collapse. Historians still argue whether the singularity even exists, whether it's real, or merely the symptom of incomplete theory. General relativity says it's there. Quantum mechanics screams in protest. String theory tries to smooth it out. Loop quantum gravity offers a bounce, but no one, not Hawking, not Einstein, not anyone, has seen inside. And perhaps no one ever will. Because maybe the closer you look, the less there is to see, not because it's empty, but because it's undefined. The center of a black hole might be the ultimate answer to the ultimate question, and the answer is question not found. Here's a final quirky thought for your journey. Some mathematicians have proposed that reality is not continuous at all, that the fabric of the universe is based not on numbers, but on information structure, patterns, rules, logic. From this view, a black hole isn't a thing, but a rule violation, a point where the code doesn't compile. You didn't fall into a place, you fell into a punctuation mark, a dot in the sentence of the cosmos where meaning breaks, and yet, there's peace here. The screaming gradients, the spinning time, the mathematical shouting matches, they've all faded. You're not crushed, you're not stretched, you're not even falling anymore, you're held, quietly, deeply, as if the universe itself needed you here, not as a victim, but as a witness. Because if black holes truly are rules, limits, then what waits at the center isn't death, it's resolution. You were never meant to understand this place as a human, or a traveller, or a scientist. You were meant to understand it as a story. This whole journey, every twist of curvature, every paradox and theory, has pointed to one final idea, that the center of a black hole is not a thing to be found. It's the edge of meaning, and you've reached it, not with a bang, but with a question mark. And now, everything softens. The spirals of space that once twisted around your mind begin to unfurl, slowly, gently, like curls of steam rising from a mug left out in the cold. You're no longer falling, not in any meaningful way. There's no more curvature to track, no more theories to decode. The voices of collapsing stars, echoing wormholes, and tangled equations are all quiet now. The black hole's secrets have nestled into place, not solved, not finalized, but folded away like a warm blanket across your consciousness. You don't need to hold any of it. Not the mass, the math, the madness. You've journeyed far enough. The gravity that once pulled your body now simply cradles your breath. Drift in that stillness for a while. Feel how light the mind becomes when it lets go of trying to understand. That question, what really waits at the center of a black hole, has done its job. It's led you here, not to an answer but to a feeling, a hush, a pause, a falling feather suspended in time. You don't have to be sure. You don't even have to remember. The universe keeps turning whether or not you unravel its riddles. Black holes will keep blinking in and out across galaxies, mysterious and majestic like cosmic punctuation. You're part of that rhythm now, so let your thoughts dissolve like stardust at the edge of a dream. Let the final echoes fade into silence, and rest. The story is complete.